One of the skills I want you to master in this course is being able to use Excel to do numeric modeling because, as I've talked about in class, that computational physics is a recognized branch of physics and an important part of being able to do physics in the modern world, because most real problems don't lend themselves to simple algebraic solutions. But in this case, since I'm not publishing what the so-called answers are for any of the spiral materials, kinematics, or you're soon to be doing dynamics, that this gives you an opportunity to check your work. So I'm going to use the Spiral Kinematics activity on page 22, where the driver of a car sees a truck and there's reaction time and that sort of stuff. So if you'll look at problem 22, you can always pause this while you are waiting or looking. So anyways, I'm assuming now that you are back and that you're ready to proceed. So what you will want to have are a minimum of 4 columns if there's a single object, and you need to populate the 4 columns: time, position, velocity, and acceleration with the initial conditions. And in this problem, that we make the assumption that the time and position start at 0. We're given that the driver is traveling 16 meters per second, which ends up being about 35 miles an hour, in case you want to know. If you ever want to know how to go from meters per second to miles per hour, multiply by 2.2, and that gives you a rough estimate. So anyways, we also know that during the reaction time, that the velocity is not changing, therefore the acceleration is 0. After you get the initial conditions in there, the next choice that you need to make is what are the time steps. And so what you need to be able to do is to take a look at the given information and come up with an idea. So in this case, we're given that the reaction time is 0.75 seconds. So whatever the time step is needs to be able to go into that in a even way. So I'm going to choose 0.25 as my time step. And so Excel makes it easy for you to replicate patterns. So if I go from 0 to 0.25, that's a step of 0.25, and I don't want to have to keep on typing in the numbers. I'll have Excel do that for me, and I'll drag this down for a ways, and it doesn't matter if I've got too many cells, because I can always go back and prune. Now I keep on looking at the given information, and the next thing that we will always do is to look at what the acceleration is if we have that given information, or if we have calculated a number. And so we know that there's going to be an acceleration of 6 meters per second to slow the the car down, and it's going to be in the direction opposite of motion, and if the car is moving in the positive direction, we will therefore assign a negative 6 meters per second that will be applied to the car after the reaction time. So it's 0, and if I ever want to copy a single cell, that same value, I can highlight that cell, go to the bottom right hand corner, drag down, and there I have zeros. And then now I want to put in a negative 6, and then I'll highlight that and drag that down. And then now we start going to the definitions of various things. And in spiral kinematics, the first equation that you work with is V2 equals V1 plus acceleration times time. And so the way we put an equation into Excel is we start with the equal sign. So we say that my future velocity is equal to the previous velocity, which is the cell right above it. So I'll click on that cell, times the time. Now I shouldn't come over here and click this time cell, because the first time it would use 0.25 to calculate, then it'd use 0.5 and 0.75. So I think you can see what the issue would be there. So what I'm going to do is multiply by whatever the time step is that I chose, which was 1/4 of a second, 0.25 seconds. So I now have that in there. What did I do wrong? I did something wrong. Yes, I did something wrong. Oops. Pardon me. What I do is, let me start all over. Okay, teachers make mistakes too. Okay, so if I want to enter the equation, I said it properly, I just didn't type it properly, that my velocity in the future is equal to, so here's the equal sign, the velocity that I had previous plus the acceleration, which is the cell right beside, times the time step. And needless to say, if there's zero acceleration, then my velocity should stay the same. Now again, I don't want to have to keep on typing that in, so I click on the cell that has the equation and I drag that down. Now for a first order approximation of position, we can say the same sort of thing. What we can say is that my position in the future is equal to, the equal sign there, the position that I was previously at, which is the cell right above, plus the velocity that I'm traveling, which is the cell right beside it, times the time step, which is the 0.25. So you see that the equation in essence is the same for both of those. Now this is a first order approximation. It won't yield the appropriate, the exact numbers for when we have accelerated motion, but that's okay as a first cut. So we'll put that in. We're going to copy that down by clicking on it, go to the bottom right hand and drag down. And so here we have it. Now if you do the problem, you know that the extent of this is that, for example, that the driver travels 12 meters during that reaction time, and so you can confirm that right there. Now during the accelerated part we're going to be a little bit off, but we know that at 3.4 seconds the vehicle will have traveled about 34 meters if you do the algebra. And if you look down here, that what I have is something pretty close, and you can also tell that you're supposed to be coming to a stop, so the velocity should be going to zero long about 3.4 seconds. So we can see that we have we're in the ballpark, and so typically if you get this close, you know that you've done it properly. Now if I do want to go back and make this more precise, the problem is that, for example, if I click right here, that this position that I'm showing is doing a calculation with the assumption that I am traveling 14.5 meters per second during that entire time interval, but that's not the case. I'm starting at 14.5 meters per second. I'm ending at 13 meters per second. So a more accurate way to do that would be to take the average of those two. So let me go back up here and modify this equation to take care of the average. And so it's still going to be equal to B2 because I want to know what I was traveling previously. But rather than just multiplying C3 times the time step, what I'm going to do is do a little calculation. I'll open up a parenthesis. It'll be C3 plus C4 divided by 2. So I add the two values together and then I divide by 2, and that gives me the average. And then I multiply that by the time step. And of course for the non-accelerated motion no change happens, but look at what happens while I copy that down, that I now have something that is a bit more accurate. And this is causing me to question, because I had 34 meters and this shows that it would be more in the neighborhood of about 29 meters that it traveled, but you get the point. So that's how you use Excel to model real problems. Enjoy.